This picture is the same as the last, except I don't have a lot of different vectors, and instead of r of t, I'm calling this function f of t. I might want to change that to r, but I'm not going to. Okay, so this is a function f of t, and f of t is typically thought of as an x of t multiplied by the I vector, which gives us a vector here, plus a y of t vector multiplied by the j vector, so we have an I and a j component. We don't have to use the I and j components. We can describe this vector in terms of ur and u theta if we just know the direction of ur at a given point. Well, the direction of ur is radial. That means it's straight away from the origin, so if this angle here is theta, our ur vector is just I cosine theta plus j sine theta. I cosine theta in this direction, j sine theta in this direction, adds up to give us the vector u sub r. Now, theta might be changing with respect to time, so that this ur vector is a function of time, but it's a vector that the moving point carries along with it. And u theta is perpendicular to ur, rotated 90 degrees clockwise from ur. And I was thinking ahead, I called that u theta, so let's, it'll be kind of messy, but let's change that theta to an r. Okay? So that u theta, if we think about it, has to be perpendicular to ur. Its dot product with I cosine theta plus j sine theta has to be 0, and its magnitude has to be 1. And it has to be rotated in the right-handed sense. Without going into a lot of detail, those conditions imply that u theta has to be, get the right pen here, negative sine theta times I plus cosine theta times j. Now, it should be very clear that the dot product of this with this is negative sine theta cosine theta plus cosine theta sine theta, and that's going to be 0, showing that u theta is perpendicular. To show that it's rotated in the right-hand sense, I'm going to leave that alone for the moment. I could explain it, but I don't want to take us too far afield. Just take my word for it that that's going to be it. And you might think it through yourself. Okay, so now we have our ur and u theta vectors. Remembering that whatever our function f of t, this angle theta is a function of t that depends on the components of our f of t. For a picture, I've got a ur u theta pair sketched on a slip of paper, and I can orient my u sub r, and of course I've obliterated the u sub r label here, but I can orient the u sub r vector along the radial line. Now, this metal strap here is oriented along the line, and here's the point of the origin, here's the point of our function at this particular instant. Now, if I rotate a little bit, then the ur vector and u theta vectors rotate a little bit. I notice that the r vector, the distance from the origin, has gotten shorter. I started here, and now I'm here. Now, if I continue to change theta, I see that again I've got to rotate the ur and u theta vectors a little bit, and I've got to pull them in just a little closer to the origin. But now from this point I've kind of got my minimum distance, which maybe is right here, and now if I rotate so that theta increases a little more, I see that my r is starting to increase, and if I go a little further out, I see that my r, my radial vector, my distance from the origin has perhaps increased a little more, and so forth, so that this UR coordinate system has to continually be adjusted, sliding in and out closer and further from the origin as the angle changes. And hopefully that'll be a useful image for you. So what I've depicted here is just a typical UR and a typical U theta.